Yeah, let's keep fighting this started. Combine bending and direct stress. Combine bending and direct stress. So, these two, when we combine these two, we need to get the resultant stress. When we combine the two, we need to get the resultant stress. So this chapter, we will be looking on these two stresses. So what you need to understand is how do you find direct stress and how do you find a bending stress? Yeah. So now, let us take for instance, we are having a bar. We are having a bar there. So on this bar, we want to find both bending and direct stress. So now, here is the center of this bar on a cross-sectional area. So on the center, exactly at the center there, with both axes, x-axis and y-axis, we apply the force. We apply axial force. Of course, this force is also on this side. It's either we push or we pull. So in this case, we are pushing. So the moment we push, what kind of the stress are we going to have on this bar? Compressive, ne? Yes. This bar is going to compress and become smaller. That is the only stress which we will have on this bar. So this one, this force, the axial force, this force with the cross-sectional area is going to give us a direct stress. Meaning for us to find a direct stress is equals to force over area. Which area? The cross-sectional area where we have applied the force. You get that part, ne? So the nature of this stress, it depends on the type of the force we have applied. If we apply a compressive force, even this stress will be compressive. If we apply the tensile force, even this stress will be what? Tensile stress. So you understand the direct stress, ne? Yes, we understand this stress. The one which now I need to explain is the bending. So okay, let us take for instance, instead of applying this force in the middle, then we apply it off center, somewhere there up, off center. There's a certain distance from center to where we apply force, which this distance is called eccentric distance, right? So if we apply the force, not exactly at the center, somewhere there, is this bar not going to bend? It will bend. Then, as we are applying there, it's going to bend about x-axis. Meaning at the end, we will be having you see, it has bent after putting our force or applying our force off center at an eccentric distance. It will bend in this manner. So now here we need to find the bending stress, as well as this side. We need to find a bending stress. So what will be the nature of bending stress on top here? Compressive, ne? The nature of bending stress at the bottom? Tensile. So now we know what are the natures of the stress, of bending stress on top and at the bottom. So how do you find this bending stress? We all know that we have this formula to calculate bending stress. Stress over Y bar. That is the formula which is supposed to use. So in this case, to find a bending stress, it will be our bending stress is equals to my over I. So the cross-sectional area is this one. That is the x-axis. This is y axis. So if we apply the force here, that is our eccentric distance. How far it is from the center to where you apply force is this distance there. So as it bends according to which axis? Is it going to bend according to y when you push? As you were pushing here, was it bending according to y axis or according to x axis? According to x axis. So meaning this I, it will be your IXX. You get it, partner? So if ever you were applying a force here, our beam was going to bend about I-axis or about x-axis? Y-axis. Meaning here we're going to substitute what? YY. But now it's bending about YXX. It is that one. Yes, it's this formula. IXX. I guess now it's bending about x-axis. You understand that part, ne? So this is the formula which you need to use to calculate your bending moment. So okay, what is this Y stand for? Yes, it will be the distance from the team to the center, depending on which one I'm using. If you will be using IYY, that will be the distance, your centroid. You get a part, ne? So let us check on the bending moment. Bending moment, is it not force times distance? It is force times distance, ne? So in this case, which force is responsible for the bending of the beam? The axial force, ne? So meaning there you are going to substitute this force. You get that part? So at what distance does it bend? At eccentric distance. That distance from there up until there. Because remember, the moment you put it in the center, it won't bend, right? So how far do you want to go away from the center so that it can bend? That is the distance, eccentric. Instead of using D, they use E for eccentric distance. You understand that part?
So it's just that small piece.
Sorry?
That distance, it's just that we don't include the other half.
You only use eccentric distance. This E, that is your eccentric distance. So now, what would be, yes, now you do have bending moment, you do have Y bar, you do have IXX. You are going to get your bending moment. So what would be the nature of your bending moment? What will be the nature of the bending moment? It will depend on which side are you referring to. If you are referring to the top side, what will be the nature there? Compressive. If you are referring to the bottom side, what will be the nature? Tensile. So now then that we have the two of them, we can add or subtract. Our direct stress, this one, due to the axial force, we get the direct stress What kind of the force we have? In this case, it's compressive, right? So if we take compressive as negative, it means here our direct stress will be negative because it's compressive. So if we were calculating a resultant stress on top here we said it's compressive, right? So it means here it will be also negative. So if we calculate at the bottom the force did not change. The force we did apply did not change, meaning the direct stress remained the same. Even the bending stress remained the same. The only thing that changes is the nature. You get that part, ne? So the nature of our bending moment here, it will be tensile. So as it's tensile, if we're calculating the resultant at the bottom here, it means instead of here being negative, it will be what? Positive. Do you get that part? So now you will be required to draw a stress graph or diagram. So when you draw, we are going to start with the bending moment, then we'll draw a resultant. Bending, then resultant. So the bending stress, you have this is your zero line. And it's going to bend about xx. Yes, it's going to bend about xx, so my zero line, it will be there for all stress. If it was bending about yy, I was going to draw here, my zero line. You get that part, Nick? So now because it's bending about xx, here is my zero line. This is 0, this is 0. So for bending stress, if we draw a bending stress, if our bending stress it was 10 megapascal, it means this side is negative 10, right? This side it will be what? Positive 10. Meaning when you draw, when you go to the left, you refer it as negative, it means you will go this side for negative 10 units. This side, you will go for positive 10 units to represent this one. This one to represent that one there. So at the end, you join the two. This one is a bending moment. So if you also want to draw a direct will only have one. Meaning the direct, if it's tensile, will go this side. If it's compressive, will go this side. This one, it will be our negative. So here, if our tensile it was 50, you'll just indicate 50 megapascal.
Not negative.
Yeah, you can also include negative, no problem. But the moment you draw it like this one 0, go this side, like this one you have already chosen as positive. This side you have already chosen as negative, even if it did not indicate the negative. Yeah, even if you indicate, that does not have much effect. So the resultant here, if your resultant, remember you need a resultant from the top and you also need the resultant from the bottom. So if the top you get that far and the bottom you get this far, you need to join the two ends. And if you check here, where the intersect is not here. So where the intersect is where you find your neutral axis. We have these two lines. The first one, this one is a centroid. This one is a neutral axis. If they want you to calculate neutral axis, they want to know how far is this distance from the centroid up until there. You get that part, ne? So we can go to the example and do example. Buenas. Which page is the example? 185. Yes. Page 185, we are having we are given that structure there. They want us to calculate the stress in the plane BC. So let me write out this one. This one is A, B, C, and D. This one is our XX, and this one is our YY. So, they want us to calculate stresses, meaning we need to calculate resultant stress at the given point, which is BC and AD. So before we calculate, for me it becomes much more easier if I have the isometric of this. We have applied the force there, right? This is X, that is X, this is Y, this is Y. Which axis is it going to bend about? X axis, ne? Meaning at the end we are going to have so at the end it's going to bend something like that. Try to see something, guys. Yeah? This one? Okay. Yes, at the end it's going to bend in that case. Ne? Remember, we need to calculate the resultant stress. And the resultant stress, we get it from direct stress and the bending stress. So it means we need to calculate the two. So in this case, how do we calculate our direct stress? Force over area. And what is the force? 36 exponent 3, right? Over 0,1, 0,1. And what do we get? Sorry? 3,6? 3,6 megapascal. What is the nature? Compressive. Nature compressive. So okay, now we do have our direct stress. It means now we need to calculate what? A bending stress. So a bending stress, previously we did find out that we can calculate it using this formula. Y over Ixx, because in this case it's bending about Xx, right? Yes. So what is the value of Y? 50. So it means now we need to calculate this two, right? Yeah, let us start with bending moment. Which formula are we supposed to use to calculate bending moment? F times E, eccentric distance. And what is our F? 36 exponent 3 multiplied by 0,015. And what we get?
540.
540.
Yes.
Is it kilo or
Neutron.
Newton? Newton meter, right? So now let us calculate our Ix, which is what? V cube over 12. And when we substitute 0,01 times 0,01, 0,1, I'm sorry for that, cube over 12. And what do we get? 8, comma 3
exponential negative 6.
mega Pascal. Is correct, ne?
No, it's not correct.
I'm wrong, ne?
Yes.
So what's the right answer?
Exponent negative 6
6
meters.
meters to the power 4. Yeah, you're right. Okay, now we have our I. So it means we can be able to find bending stress. So our bending stress will be 8,333 exponent negative 6 multiplied by, said y is equals to 0.05, ne?
Yes.
Come again?
No.
Oh, this one is I, ne? What is our bending moment? What is our bending moment? 540, yes. 540. Then, this is correct, ne? So, what about our I? 8,333 exponent negative 6. And what you get there? 3,24 megapascal. I do not want to write before you tell me, hey. So, okay, what is the nature of this bending stress? It depends on the side, ne? If you are looking from the top side, it will be what? Compressive. If you are looking from the bottom, tensile. So, okay, in this case, they want us to find what? AB, right?
Yes.
And here is AB. AB is there. This one is what? BC. So AB is this top here. ABC. ABCD. ABCD.
Yes.
A, B, C, D. So they want us to find AD, right?
Yes.
So an AD is here on top, right? So on top, is it compressive or compressive? So our direct stress is compressive.
Yes.
And meaning stress at AD, it will be direct stress, which is compressive,
Yes.
minus bending stress, which is also compressive. I'm correct, ne? Then this one is 3.6 minus this one is 3.24. And what do we get? Negative 6.8484 megapascal. So all in all, it means we have 6.84 megapascal compressive. We together. So now they want us to calculate the stress where?
BC.
BC is the bottom, ne? So is the bottom compressive or tensile? Tensile. It means the bending stress at BC is equal to tensile. The bending moment is tensile, meaning it's positive. What about the direct? Negative. And what do we have?
3,6.
This was what?
3,6.
3,6 minus 3,24. Right, ne? You are giving me now.
3,24 minus 3,6.
It's opposite. Masha, where's the 3,24 minus 3,6, ne? And what we have? Negative 0,36. Meaning all in all we have 0,36 megapascal compressive. You get that part, right? So now we need to draw those stresses. We need to draw those stresses. Machine, where's it? Oh, today I'm no longer talking Chinese. So, okay, in drawing these stresses, let us start with direct. I'll start with direct. No problem, but I'll start with direct. Again, direct we only have one, right? Which is what? Compressive, right? So it means it will go this side because this is our zero line. It will go there. So from there to there, I'm just estimating that is 3.6 because of the space. Megapascal. So from there, we draw our bending. So here is my zero line. This is my zero line. At AD, what is the nature of the stress? It's compressive, ne? So compressive, because it's negative, will go this side.
6,84.
Sorry?
6,84.
6,84
Yes.
megapascal. And this, what is the bending stress this side?
Compressive.
Both of them is compressive.
Yeah.
It's compressive at the bottom. And now we're at BC. It's tensile, eh? It's positive. Sorry? Now we are talking about bending stress. But what is the magnitude of bending stress? I will teach calculate bending stress. This is a bending stress, right? So the value you have given me here, it's a resultant. I'm talking about bending. Masha. Bending stress is equal to 3,24 megapascal. It's compressive, right? And this other side is tensile, right? The same value, because this is bending. So we'll join these two. And as we join, these two, they're going to intersect on this centroid. You get that part, ne? So now we are drawing what? The resultant. So this is my zero line.
Are we drawing according to scale?
We are not drawing according to scale, but you can estimate. You can estimate. If you check, for instance, now we are having two stresses which we need to draw. Can you see? Obvious, this one is bigger than this one. So meaning even when we draw this line, it must be a little bit bigger than this one. Yes. So now, what is the resultant stress here? AD.
6,84.
6,84. Positive or negative?
Negative.
Negative 6,84. And down here,
0,36.
0,36 megapascal. This one megapascal. Then we join the 2 points. So if you check where the direct stress is equal to bending stress, that is our neutral axis. And this on this drawing, we do not have that point. That point, it happens when this diagonal line, it touches the zero line. For instance, on this case, this diagonal line touches the zero line here. So in order to find that one, you can extend there. You can extend there. You also extend there. Can you see the intersect there? Can you see where the intersect? It means from there to there, or here at this point, is where there is our neutral axis. So how long from this point to that point? That is another question which you will be expected to calculate. But so far, do you understand? You understand, eh? So okay, let us check how to calculate this point here. Calculating that point then. We said at this point we said direct stress is equal to bending stress. This one, it's only applicable on what? At the resulted graph, ne? Yes. So in this case, our direct stress, we did calculate. I can still input direct stress there. Bending moment is M Y over I, right? So initially, we were using this Y. When we calculating the bending moment here, we were using Y from there up until there, from up until to the centroid, right? So now, because we are equating the two, which is found on this graph, it means our Y, it will be that distance from there up until there, which we can name it YO. You understand, eh? So do you understand how to get your neutral axis?
Yes.
So this Y, it will be your neutral axis. And please, do not mix this Y and as much also as that one. There are two different stories. Is there any question? YO. Against YO, they will tell you to find the neutral axis. Remember, there's a difference between neutral axis and the centroid. Centroid is the center of the object. Neutral axis is where bending moment is equal to direct stress. You understand that part, ne? So they will tell you to calculate that distance of a neutral axis. So if bending stress is equal to this one, therefore this is the formula. We can substitute this one as a formula. So, but what about this Y? The Y is the distance from the centroid up until the neutral axis.
So it must be greater than 50.
In this case, it will be greater than 50. Remember, it's not always which it will be greater than 50. Sometimes you may find that this one, instead of being the stress here, you may find that instead of being compressive, it's tensile. And once it's tensile, it means the graph will go something like this. Therefore, this distance, it will come inside there. Yes. So the reason now both of them, they are compressive. Maybe I should explain that one. We are done with the example. I just want to explain why both of them are compressive. I'm good in drawing. Eh? If I did drafting, I was gonna get total here. Yeah. As long as you can see something. So, okay, the reason you find that the reason that you find that the resultant is both compressive is because the reason why both of them they come out as compressive. Remember, when you push here, when you are pushing there, right, with axial force, when you are pushing, it gets compressive on both sides, right? The moment when it starts to bend, it will be this one, right? It means this one, this side, as is bending, although it's under tensile, it's not that tensile because the compressive. Do you get my point? agree here is compressed, ne? In this portion here is compressed. So as it bends, the tensile stress here is moving from being compressed to tensile. So it means it doesn't actually reach that position of being tensile.